Another method used to solve systems of equations is the method of elimination. It's also sometimes called the method of addition because we're going to add the two equations, it turns out, in order to eliminate one of the variables from the system of equations. Here's how it works. We look at our two equations and we are trying to create a situation where we can add the equations and eliminate a variable. Now, for that to happen, we have to have the coefficients of one variable or the other differ in sign only. Now, if the condition doesn't already exist, and it doesn't here, then we'll have to multiply through one or both of the equations in order to create the situation. Now, the situation I'm talking about is that the coefficients are alike except for their signs. So they differ in sign only. Now, we can create the situation here very easily. In equation 1, all we need to do is multiply through by -1. And we'll have negative x up here and x here, and when we add the equations, the x's will go out. That's the idea. So we have equation 1, equation 2, and equation 1 I'm multiplying through by -1. It'll just change all the signs. And we'll bring down equation 2. Add the two equations. The x's go out as expected. Then 1y plus 2y is 3y. 5 and 4, 9. Dividing on both sides by 3, we find y to be 3. Now, once we've identified the value of one variable, we identify the other variable in exactly the same way that we did before. That is, we take this value for y and we put it into one of the original equations and solve for x. Let's do that. I'm using equation 1 here, and I replace y with 3 and solve for x, and I find x to be -2. So the ordered pair -2, 3 solves the system of equations. Now, you may recognize this as being the same little system of equations that we started with in the previous section when we solved by substitution. So we can use either of these methods on this particular system of equations. Suppose we have a system of equations that looks like this. Now, we're going to use the method of elimination, which means that we're trying to identify coefficients of x and y that differ in sign only. I don't see that situation here. I don't see it here. So we're going to have to manipulate a little bit, that is, multiply through one or maybe both of the equations to cause that condition to exist. Now, if we sort of attack this problem by looking at the coefficients of x, we're going to need to multiply in both equations. Now, the least common multiple of 2 and 3 would be 6. So if we multiply in this equation by 3 and in this equation by 2, then we'll have 6's as the coefficients. Now, in one of them, we would have to multiply by a negative value to cause a sign change to occur as well. Well, it kind of looks like to me that we should attack the coefficients of y because we need only multiply in equation 2. The sign changes, the sign difference is already in place, so we don't have to worry about that. All we need to do is multiply in equation 2 by 3 in order to create the condition that we want. Well, to keep things organized, I'm going to bring down equation 1 here. And then in equation 2, I'm multiplying through by 3. So 3 times 3x, 9x, 3 times y, 3y, and then 3 times -5, -15. And I'll draw the line and add the two equations. 2x and 9x, 11x. The y's go out as expected. -7 with -15 is -22. And then when I divide through by 11, I find x to be -2. But if x is -2, I find y by back substitution. I replace x with -2 in one of these two equations. I've chosen to replace x with -2 in equation 1. So here's equation 1, replace x with -2 and solve for y. This becomes -4. Adding 4 on both sides, I find -3y to be equal to -3, so y is 1. When x is -2, y is 1, and so this is the solution to the system. Well, with systems of linear equations, there are several possibilities for solutions. Now, we looked at a number of situations where the graphs would cross, and we have one ordered pair that solves the system of equations. There are other possibilities. Let's have a look at them. Now, the situation that we've seen in the past many times is that the graphs cross and the solution is here at the intersection point, so we have one solution to this system of equations. Now, this system is called a consistent system because a solution exists. Another possibility is that you begin to graph the first equation, and let's say the graph looks like this. And then you start graphing the second equation and you begin to plot points that are right on top of the first one. So it turns out that the second graph is right on top of the first graph, so every value that solves one of the equations solves the other one. So we have an infinite number of solutions to the system of equations, so a many solutions case. Now, both of these are consistent systems because they have solutions involved in them. The third possibility is that the two graphs will be parallel. And if they're parallel, they'll never cross. If they never cross, no intersection point, and therefore no solution to the system of equations. It's important for us to be able to recognize these two kind of funny-looking cases when they crop up algebraically. We can see them easily here graphically, but how does this make its appearance algebraically? Let's have a look. In this system of equations, if I were trying to solve by, let's say, elimination, then I would be creating a situation where the coefficients are the same except for sign. I look immediately at the two equations and I see, oh, I can attack the coefficients of x rather easily. I'll just multiply in equation 1 by 2. So multiplying here by 2, I get 2x and then minus 4y and then 6, you see. All right, so now I have the situation I'm after, and I'm only concentrating here on the x's, and I draw the line and add, and here we go, 2x minus 2x, 0x, as expected. But then we look over here at the y's and we say, uh-oh, because minus 4y plus 4y, that's 0y. So all of the terms over here have disappeared. We have simply 0 over here. And on the right, we have 6 and 1, 7. Now, when both variables disappear from the system at the same time, you look to see whether the resulting statement is true or false. And that's the thing that tells us the kind of system that we have. Now, this statement, 0 equals 7, is a false statement. And since it's a false statement, it means there are no solutions to this system. It is an inconsistent system. The graphs here turn out to be parallel. And we could see that if we solved both of these equations for y. You see, we would see the same slope but a different y-intercept in the slope-intercept form if we went through that kind of analysis. Now, the other situation would be where the two, the adding causes both of the variables to disappear, but the resulting statement turns out to be true. Now, that would happen if I make a little change here and just cause this to be, oh, let's say, negative 6. And then this would be negative 6. And then when we add the two equations, all this business disappears. But when we collect the 6 with negative 6, we get 0. You see? And then, so the variables have disappeared, but we get a true statement. And when we get a true statement, it means we have infinitely many solutions to the system. And actually, it implies also that the two equations are equivalent to one another. And we can see that pretty easily as well, that we can manipulate either of these equations into the other without very much difficulty. If we divided through this one by negative 2, we would get that equation. Divide here by negative 2, we would get x. Divide here by negative 2, we would get negative 2y. Divide here by negative 2, and we would get 3. So the two equations are equivalent, their graphs are identical, and therefore we have an infinite number of solutions. Here's a word problem.
50 gallons of 70% acid solution are obtained by mixing an 80% solution with a 50% solution. How many gallons of each solution must be used to obtain the desired mixture? Well, it turns out that in building a system of equations to solve this problem, we simply think of the mixing process itself. That is, the system of equations will emulate the mixing process. Now imagine here, we have some 80% acid and some 50% acid. We don't know how much, but we do know that when they're mixed together, we get 50 gallons of 70% acid. Now, think of this in an equation format. You see, simply let X stand for the number of gallons of one liquid and Y the number of gallons in the other liquid. And now we can build our equation. You see, we know that there are 50 total gallons, so it must mean that the number of gallons X that we have plus the number of gallons Y that we have is equal to 50 total gallons. That becomes the basis of equation 1. You see, often the equation 1, or one of the equations in our system, is a relatively trivial one. It's relatively obvious. Gallons plus gallons here is equal to total gallons. Now our second equation is based upon the intensity of acid involved. And actually it's based upon the amount of pure acid in the first container plus the amount of pure acid in the second container is equal to the amount of pure acid in the mixture. Now the amount of pure acid in each container is found by multiplying some number of gallons times the percent of acid. So it's gallons times percent plus gallons times percent is equal to total gallons times resulting percent. Well, in the first container we have X number of gallons. We multiply times 80% or 80 hundredths. In the second container, Y number of gallons is multiplied times 50% or 50 hundredths. And on the right we have 50 gallons and the percent acid is 70, so it's 70 hundredths. Well, this will become equation 2, but it might be worthwhile to go through a step or two to clean it up, make it look a little more sensible. Multiplying throughout this equation by 100, that is, multiplying 100 into each of the terms, would clear the decimals. It would just move the decimal points 2 places to the right. And then, of course, we would rewrite as 80x plus 50y is equal on the right to 50 times 70, or 3,500. Now this is equation 2. Notice we could, if we wanted to, divide throughout by 10 and simplify the equation even further. But let's suppose here that we don't see that. Now our prescription, if we're going to solve by the method of elimination, would be to try to cause the coefficients of the x's or the y's to be the same except for sign. Well, let's attack the coefficients of the y's here, and in doing so we would multiply in equation 1 by negative 50, giving us this. Now we'll bring down equation 2 and simply add. Now notice that the y terms add out as expected, and with the x's we get 30x, and on the right we get 1,000. Dividing on both sides by 30, we find x to be 33 3/10. In order to solve for y, we end up back substituting into one of our original equations. Equation 1 seems to be a bit simpler, so in equation 1 we'll replace x with 33 3/10. Now of course we'll subtract that amount on both sides of the equation to find y to be 16 7/10. Well, now we have our answers. We know that 33 3/10 gallons of the 80% acid solution and 16 7/10 gallons of the 50% acid solution are needed.